Morning, everyone. I'm John Berkebile, as you just said. Quickly overviewing some of the work that we've done recently in this respiratory sensing field, and to try to give some motivation as to why we care about respiratory sensing. I feel like it's not that difficult to motivate. If anything, the past few years have kind of shown us why it's important, but I just want to highlight that there are several contexts in which we care about respiratory sensing. For instance, the most obvious case is in respiratory disorders, where you have either restricted or obstructed breathing. This can come about from various different diseases and conditions, chronic obstructive pulmonary disorder being one, or respiratory muscle weakness being another. All of these kind of can manifest in different alterations of your breathing pattern, and we can use sensors to actually try to track the progression of these types of diseases, even in completely different context of mental stress. Think about your fight or flight response, how that affects your respiration, how you can actually get an insight into an individual's stress response, how we might be able to tailor medication or different therapies to these people. And then also the cardiorespiratory coupling. So heart failure is a huge issue, especially in the United States. And as cardiac function declines, often what happens is pulmonary edema or pulmonary effusion. You get fluid in and around the lungs, and that can also kind of inhibit breathing and affect your respiratory pattern. So there are several contexts in which we care about respiration, and the markers that we have of interest are also of interest. Respiratory rate is being the most widely used respiratory marker. Often when we think of respiratory sensing, we kind of just confine that to respiratory rate monitoring. It's not a very specific term, respiratory monitoring, generally speaking, because it also leaves out volume measurements, which kind of culminate in a more comprehensive approach to looking at respiration. You miss out a lot of information if you just focused on respiratory rate. In fact, there was a review paper that's very well cited from 2003, so 20 years ago, that was talking about the ideal respiratory monitor, including both rate and depth information, kind of a comprehensive look at respiration. And we have to think, have we addressed this today with our modern sensing modalities? Have 20 years since passed, have we now developed these capabilities to be able to sense not only respiratory rate, different timings, but also volumes? And I think what we find is when we look at current wearables, we can get limited measures of respiration, but it's very difficult to actually kind of capture that comprehensive view of respiration. So there are several different types of sensors that are commonly used, usually capturing the mechanics of the chest wall in response to breathing. And these can be integrated in different form factors that can be great for actually wearable circumstances. But I think what we find is whether with this approach or with a more physiological based approach, where you look at different modulations that the respiration has on signals like PPG, photoplethysmography, or ECG. With either of these approaches, you're still only getting, again, typically respiratory rate information and not kind of capturing more of the volume and other aspects of respiration. And that's because volume monitoring is very difficult, not only adding on top of that, doing it unobtrusively. When we think about the equipment that's used, it can be commonly constrained to just clinical environments because of its specialized nature, because of the bulkiness, even the at-home devices that you can take, whether capnography or spirometry, they're still not very useful and convenient to do. People are not going to be wanting to use these time on time or for continuous measuring. So with this, we're trying to propose impedance pneumography, which is a well-known technique for capturing the impedance changes of the thorax to actually capture your tidal volume being one. So it actually grants you insight into a respiratory surrogate signal itself, rather than kind of these downstream measures. So, and it does that by capturing both the volume of the lungs and also as your thorax expands during exhalation and inhalation. And how we measure this is we place 4 electrodes typically around the chest, and we can do this in a couple ways. You can often see single frequency excitation, where you use just a single electrical current stimulation, and you measure the voltage in response to that, and that's how you get your bioimpedance signal. But you can also measure at different frequencies, and you see you'll have different frequency responses, which can go through different pathways. So extracellular fluid being captured by lower frequencies, and both intracellular and extracellular fluid captured by higher frequencies. But yet, no free lunch. Even with this method, there's still been in the past a burden of calibration. So typically what's done is you do a subject-specific calibration and potentially even a posture-specific calibration, because you see a lot of different variation. When you think about a subject, depending on their height, their weight, where the sensors are placed, this can affect what the impedance resulting is, what the max tidal volume is, things like that. You can see you get great variation between subjects and also in individual subjects. As you change posture, the way that your chest actually moves during respiration is also affected. Your fluids are redistributed throughout your body. That can also affect bioimpedance as well. And so our goal is to leverage multimodality to try to reduce these different dependencies and ultimately have a more generalized approach to tidal volume estimation. And so coming back to this, we're adding in now an accelerometer placed in the xiphoid process. That could also be placed around the sternum as well, or other places around the chest to try to capture another measure of this thoracic expansion. And so maybe we can normalize that effect and capture or isolate more so the effect of the change of volume of the lungs. So for to be able to capture this, we developed a prototype, I guess, several years ago at this point. It's been validated in a clinical population of heart failure, where we took it and we applied it on different subjects to continuous monitoring sessions. We got dual frequency, so like I said earlier, you can measure low and high frequency characteristics of the impedance to get different aspects. And that is enabled by the 805940 bioimpedance front-end chip that we use. This also comes with 2 IMUs, 2 temperature sensors, and this is a dual board design, so really we're only talking about these measures in this study, but this also can capture 4 channels of lung sounds. So that's what we used in the clinical population. But this could be worn. This was made to be worn on the arm, and you can place the sensors as needed. This is more of a prototype to kind of validate where, what placement we would need and things like that, so it could be condensed further in the future. So in this study, we captured, we used our system in 10 healthy subjects, along with concurrent spirometry and in a controlled breathing protocol. So we had a standard breathing rate throughout at different, while modulating the different breathing intensities. And we did this in 3 different postures: sitting, supine, and standing. So we did a conventional configuration for the electrodes here, where it's on the mid-axillary line, right at the armpit, essentially. And that's been shown to be well correlated to lung volume. And our goal is, as I said earlier, to try to fuse these modalities to enable a more generalizable model. And so briefly, we'll kind of walk through the actual signal processing pipeline that we used to get to our models. So we start out with resampling and aligning all of our signals and isolating with a band pass to the frequencies of interest, the respiratory band. And then we process the IP signals. So we have 2 frequency IP signals, and we go breath by breath, essentially cycling them, and we form signal quality by essentially taking a moving window of these breaths, forming a template of them, and then comparing using correlation without, so we can identify breaths that are not breaths, that are artifacts rather. And then we use the amplitude of this as our correlate to tidal volume. And additionally here, this is where we fuse in the accelerometer signal. So we take the 3 axes of acceleration that we measured, and we use PCA to condense that into a single vector, which captures the maximum variance, which would be most related to respiratory activity. And we do that same processing pipeline where we treat it as its own respiratory surrogate signal, but yet that one's more sensitive to artifacts, so we expect more of those breaths to be removed, which would be important for later. And then we also use it in a different way. We use it more as a normalization on the IP signal. So we use the IP signal, the breaths that we detected there, to kind of segment out parts of the accelerometer signal we're interested in looking at, because where we know a breath is, and we use an envelope of that signal to normalize our IP amplitudes. And that's kind of in effect to try to generalize across different subjects and across different postures. And then finally, we take this barometer signal and we process and we get our reference tidal volume values. And after all this, we condense this along with demographics, which should help us better kind of compensate for, okay, different heights, different weights. We'd expect different lung capacities. And we trained ridge regression models for 3 different feature sets. The first one being our baseline, where we just use the IP signal only. And we would expect this to not generalize well based off what we saw earlier. For the second one, we include all the features except for the ADR amplitude, which remember we said that we process that as its own respiratory surrogate signal, but it's going to be more sensitive to artifacts because it requires a very clean chest wall motion. So you can kind of take that as that would be the cleanest data only, trying to get the most accurate estimates. And then, that would be for all features. Sorry, model 2 would be without that. So it would be trying to retain as much data as possible with some of the normalization methods, or normalization features, but not all of them. And then we used leave one subject out cross-validation, and we Blair out meta-analysis, which we'll see here on this slide. So we can read, but this is model 1, so this is our baseline performance. We got an R squared of about 0.69, with mean absolute percent error is about 32%. So this, with this method, we can see it doesn't really generalize that well. You can clearly see different. It does not condense all the subjects well. But as we add in a couple of those normalization measures and the demographics as well, we see that our R squared jumps up to 0.77. So we already have an improvement. And this is over the same amount of breaths, because for the last jump to model 3, where we actually reduce the amount of breaths because we have a more limited feature sets, and so we're including that more sensitive accelerometer signal, that we limit the amount of breaths that we include, but we include only the high quality breaths, so we know that we're getting better features for estimation. R squared is 0.84 with mean absolute percent error of 21%. So we can see that as we include these modalities, that we can actually improve our estimation, and we can have a trade-off also of whether we want to capture as much data as possible and use as much data as possible, or if we care more about actual specificity and accuracy. And so how can we improve this further? How can we leverage more modalities? How can we leverage the modalities we already have? So we talked earlier about there being the physiological approach where you use signals like ECG and PPG, and also so SCG is the seismocardiogram, which measures the chest. It's also measured with an accelerometer, but captures the cardiac information rather than just the chest wall motion of respiration. So all of these are actually modulated by respiration, and they're usually just used for respiration rate, but some recent work has started looking at respiratory volume estimation. And so augmenting what we currently have with some additional signals, while also giving us insight into the cardiovascular function of the patient, could also enable better respiratory estimation. And we've also done some work on optimizing form factor. So as you saw, the electrode configuration we used is not very ideal for wearable settings. It kind of requires you to span across the body, which isn't too dissimilar from a belt that has already been used before, something like that. So in this case, we developed an electrode patch that you can use, which would be a much smaller form factor. And again, we could get rid of the separate device from there. And again, what can this enable us to do now that, assuming one day we'll be able to get this accurate and precise volume monitoring? We saw earlier that there's a ton of context in which this is relevant for, and this would allow us to extract continuous markers of respiratory decline. So rather than having this intermittent kind of view of respiration, or maybe just a kind of cursory glance through respiratory rate, we'd be able to continuously track the decline or acute events that may happen that would be very, very important for clinical experts. And additionally, this can be used to inform other modalities. So in this case, we use other modalities to kind of help inform IP, and pneumography can be used in other cases as well. So a talk that'll be given later today by Antonio actually uses this to inform the lung sounds that we capture with our system as well. So you can use flow correction. You can actually derive the respiratory flow from this IP signal and use that to correct lung sound amplitude features. So again, trying to add context to the sensors and the signals that we measure to enable better. Are there any questions?